Hi, I'm Alex, and today I'm excited to show you ThermalRouter, our tool for enabling users to design thermally sound devices. This work was done by myself, Boris, Shan-Yuan, Daria, Joyce, and Svitlana in Pedro's lab at the University of Chicago. Now, what do I mean when I say thermally sound devices? Let me use this example to demonstrate. Here, a maker has 3D printed 2 lamps of a fire-breathing dragon that they found on Thingiverse. The maker, excited to brighten up their room with some custom decor, turns their lights on. However, after just a few minutes, they find that one of the lamps that they just spent hours printing has collapsed. Now, the difference between these lamps is that the lamp on the left is the default model from Thingiverse, but the lamp on our right has been modified by our CAD tool, ThermalRouter. So let's find out why can the version made with ThermalRouter withstand the heat. It's because ThermalRouter automatically embeds the maker's model with heat channels that dissipate the heat. They're made from commercially available, thermally conductive plastic and act as an embedded heatsink. We made ThermalRouter for 2 reasons. First, makers often 3D print objects that interact with heat sources, whether it's a lamp, a motor, or a CPU. And unfortunately, 3D printed materials are insulating, and they often have low melting points. And then secondly, heat transfer itself is just plain unintuitive. How many makers want to do something like tediously set up a finite element analysis prior to printing their designs? What I'm describing is quite literally a thermal engineer's job, and unfortunately, current tools fail to empower makers with the domain knowledge of engineers. And so we made ThermalRouter as a CAD tool in order to help novices with making their designs thermally sound. So let's see how this works. Consider a maker that's making a Raspberry Pi gaming case. While playing, the Raspberry Pi overheats. Now, they could go back and click on the built-in finite element analysis and attempt to design and simulate a solution themselves. But simulation has a steep learning curve and requires many inputs from the user. Any inaccuracy here can result in dramatically wrong solutions and frustration. Moreover, finite element analysis alone doesn't actively help the user to solve their problem. So let's see how ThermalRouter both actively helps the user and simplifies this process of running simulations. So the user runs ThermalRouter, which we implemented as a plugin for Fusion 360. It guides the user by asking for information that informs the tool to generate designs and run simulations. So first, the user selects the heat source and says its temperature is 80 degrees Celsius, and then later selects the parts in the model that are exposed to air. Then the user lets ThermalRouter know which parts can be embedded with heat channels by selecting the top and bottom of the case. Immediately, ThermalRouter begins generating designs with thermally conductive material branching out from the heat source, like these. Now, you might be asking, why not print the entire design from this material? And it's just costly, basically. While this is available as a consumer product, it's $250 for a kilogram spool, so 10 times that of PLA. And often, you really don't need that much material in order to dissipate the heat. So we strategically generate these types of branching patterns in order to spread the heat and let the user specify their budget. For example, dragging the cost slider down will reduce the channel thickness, while dragging it up will apply material more generously. So after these very simple inputs from the user, ThermalRouter now automatically simulates the performance of the original model, followed by these many variations of branching heat channels, and then picks the design that best meets the user's specified goal. By default, this is lowering the maximum temperature, in this case the CPU, but it can also be something like smoothing the thermal gradient in order to reduce hotspots. So the user can now go print and play because the heat channels have cooled down their CPU. A benefit of our approach is that ThermalRouter uses existing CAD operations. This means its output is editable by the user. For example, if a user doesn't want a heat channel somewhere, they can roll the model history back to before ThermalRouter's changes, manually split that area off, and then roll the timeline forward to automatically update the heat channels to avoid this area. Or the user can directly interact with the sketches generated by ThermalRouter, like this. Now, importantly, ThermalRouter can be used throughout the prototyping process. It does not have to be the last step. In fact, this user, satisfied with cooling their CPU, wants to add haptics to their device with some rumble motors, which themselves generate heat. So they run ThermalRouter again with the new heat sources selected, and the software generates additional design variations for the user, and so on. Now, there's two key software steps for ThermalRouter to work: generating heat channels and running simulations. For info on how we run simulations, please refer to our paper. So generating heat channels follows a simple process of starting at a heat source, generating a branch, patterning that branch radially around the heat source, extruding this pattern to 3D, then doing a Boolean intersection on the modifiable parts, repeating this for a set of different parameter variations that depend on the user's input, and then repeating this for all remaining heat sources. And I want to emphasize that while these patterns are simple and not necessarily optimal, they're effective at dissipating heat and can be printed in these multi-material prints with ease. Now, ThermalRouter isn't just for rigid objects like I've shown up until now. If a user's working with soft materials like silicone, they can check an optional box that lets the tool know that they'll need molds. So ThermalRouter generates molds with an additional step of cutting the desired object out of a solid block so that the object can be cast. For example, this user is making a soft case for a Raspberry Pi with thermally conductive silicone. So let me show a few creative ways that ThermalRouter helps users. This fan's motor heats up and causes its fixture to melt. ThermalRouter fixes this by adding heat channels around the motor. As you can see, these dissipate the heat buildup by routing the heat away. This silicone phone case overheats the phone, but adding dissipative heat channels cools it down. And of course, the fire-breathing dragon lamp, which went from crumpling in minutes to surviving a 24-hour stress test. So the digital fabrication community, our friends in this room, have examined how to embed domain knowledge into novice-friendly tools to help design objects that are mechanically functional. However, up until now, users haven't had tools that automate the challenges of heat transfer. And so this is what we try to tackle with ThermalRouter. I want to conclude by highlighting something interesting. ThermalRouter automates technical challenges. It was never designed primarily to be an educational tool, yet we've been running some workshops where we hand this off to makers and tell them, address this heat issue, and they step away from the tool telling us that they've learned something from it. We attribute this to ThermalRouter's interpretability of the solutions and ability for the user to directly modify its output. And we see tools like this as a way to empower users to both automatically create practical solutions, but also to grow their skills and intuition so that they might become better makers even in the absence of these tools. I want to thank my collaborators that really made this work possible, and thank you all for your attention. I'm excited to take your questions.
Hi, Alex. Great work for us, photography from MIT CSAIL. I have a question about... Yeah, okay, thank you. How do you specify the temperature limit? It's like, how do you control that, okay, this device needs 40 degrees Celsius as a limit? And can the user control it as well?
I'm not sure if I'm hearing exactly.
Okay, so like, for example, in this 3D model, how do you know that this model requires a limit of 40 degrees Celsius?
I see, okay. Yeah, there's a variety of ways that users can figure out what the temperature of that part might be. The best example is with something like a Raspberry Pi where you can look at the logs and actually see what the temperature of the CPU is, but there's alternative methods. A basic thermometer could be used as a probe, a thermal camera if you're a more advanced user that has that, or even just looking at data sheets to see kind of what the maximum temperature you might be looking at. A really basic one would be touch as well. I mean, you can just go off of feel in some cases.
Got it. Yeah. Thank you.
Hi, Yuni from MIT. I wonder, right now, the applications seem to be more about heat dissipation. I wonder whether there are like other applications that's kind of like precise routing for heat. So for example, if you have a heat source and then you want it to heat up something else. And also, can you put it into fiber form factor and put it on garments?
Yeah, I think that's kind of the natural extension of this work. So this is really aimed at helping the makers with these kind of low fidelity heat issues. I really envision putting this into something that's less about dissipating heat and more about using heat in like interactive ways, exactly. How can we move that heat from somewhere where it's bad to somewhere where it might be useful, perhaps like providing haptic feedback or something like that to the user.
Yes, yes. Thank
Thank
you.
you.
Hi, Alex. Thank you very much for your talk. Very nice work. It's Raul from MIT Svitlana UIST23. And my question is about, for example, in the controller, I don't know if I understood well, how do you design the shape for dissipating? I mean, you have there like this kind of a spider to dissipate the heat, but
yeah.
Do you have any idea of how to design the optimal shape to dissipate the heat?
I see. Okay, so we draw inspiration from works directly in heat transfer that use these similar kind of branching heat patterns. So essentially collecting this heat at the source and then trying to spread it to a wide area. Exactly. And with that, we're kind of constrained by the user's budget and then also things like printability. So that's why these channels are pretty thick. Yep.
Okay, thank you very much.
Hi, Alejandro from UIST. I have two questions. The first one is, have you considered adding a cooling source to your simulation? Because my lab, we just like print it, put a fan, let's see if it holds. We're not going to do a finite element analysis for simple prototypes. Then maybe you can add a cooling source as well to simulation.
Yeah.
And the second question would be, have you considered any aesthetic elements to your exploration? Like, for example, like crafters, of course, we like to paint things. So maybe there's a way to heat stimulate the paint to essentially evoke different patterns and include the stencil patterns into the aesthetics of the controller, for example. So it shows lightning or something as it heats up.
I see. Okay, to answer the first question, yes, we've looked at exploring cooling also. It basically works the opposite. The heat just flows in a different direction. In our paper, we have an example of someone that made a like a silicone ice pack that better, capture or draws heat from the user and cools them down using these kinds of soft and stretchable heat channels. And then to answer your second point about the aesthetic elements of it, it wouldn't be too hard to extend this into that area if you add something like a thermochromic paint. Yeah, and probably could be integrated into the tool as well. Yeah.
Super cool. Thank you.
Thank you. I love it.
So hello, I'm Doha from Aarhus University. So I was wondering what kind of temperature threshold, like the top limit, did you consider? So was it the glass transition of the filament that you're using? So this is the first question. The second question is, so do you have any analysis that you just compare this ThermalRouter project with any? Yeah, as far as I understood, you are just using conductive thermal conductivity. You're just using the thermal conductiveness and also for, natural convection, right? So you're just actually creating some traces for the heat conductivity, and you're just actually forcing the material for the natural convection. So did you compare the forced convection and the natural convection of your system? So I mean, I was wondering why, I mean, is it really effective, like compared to the forced convection you got me? So,
yeah. Okay. There was a lot there.
Sorry for that. Because by the way, it's a really great project. I really like it because, like, for the do-it-yourself project, it's awesome.
Thank you.
So,
I can start with the back half of that question in terms of this kind of compared to like conventional ways of cooling things down or doing like forced convection. What we do is we embed these channels directly into the model. So we like this approach because users don't have to redesign around something like adding in a heat sink, which in this case, this is exaggerated, but if a user adds in this additional material, then they have to probably change the fit of their design, whereas ours, it's kind of embedded directly inside.
I actually have to stop you from answering those questions because the session is over, but I want you guys
please.
keep talking.
I will find you.
Okay.
No, we're done.
Okay.
Sorry, the session's over.
I said I will find you.
Oh, I'm sorry. I think that I had a question and I was like, okay, perfect. Thanks everybody. This is a great session.
Thank you.